Good morning. Good morning. Okay, I'm getting ready here. We're going to just share the link with you guys and hope that you're having a good morning. Okay. All right. Hopefully, I'll get started in just a minute. Let me check my audio. See if I got my audio. You guys see audio? Yes, it seems to be working. Let me see if I get anybody coming. Oh, yay. Good morning. Okay. All right. So we'll get started in just a second. And yeah, let's see. I'll put this, switch this. Oh, I learned a new trick. Alt N. It didn't work. Okay. Hold on. Let's try one more time. Alt N. There it is. Okay, cool. So you can actually switch screens quickly. Okay. Gives me a little, but anyways, good morning. Yeah, I tried something new today too. Let's see if this works, but I'm streaming in a higher definition than usual. So not sure if that makes any difference to you, but maybe it'll be clearer when you look at the YouTube video. So just hanging out here. Anybody have any questions actually before we begin? Any questions? I can answer questions for you. Got a couple minutes before class will start. Otherwise, I will sip on my coffee here. Draw a little picture here. So over the horizon, right? The sun is rising. Oh, it's brilliant. He's smiling too, but you can't tell. Okay. All right. This is silly. Yes. No questions. Okay. Well. All right. We got people. We got people. I got people. That's great. Okay. So I know. What a job. What a job we have. Okay. So we have an agenda. I'll wait one more minute. Anybody have questions? No questions? We got a few people now. So we're moving right along. We're actually in great shape. We've got the asteroid that is supposed to pass on April 29th. No, I'm not. Do you have a link, Sean? That sounds really cool. Asteroid. We have asteroids passing by all the time, but let's see. Near-Earth Object, April 29. An asteroid half the size of Everest. Huh. Nearly half the size of Everest. How can you see it? Ooh. Okay, so let's see. Official name, 1998 OR2. It's just going to be, oh, well, we're not going to see it. We're not going to see it when it passes. Oh, but there's actually a virtual telescope project. That sounds pretty cool. About half the size of Mount Everest. Okay. So it will not hit the Earth. Okay. Don't worry about that. Not going to hit the Earth. Not going to hit the Earth. Okay. So there is a virtual telescope project. Oh, this is actually a pretty, never mind. Okay. Doomsday Countdown. No, don't worry about that. The Sky Live. Okay. Let's see. View map real time. Closest distance. Okay. So actually, why don't we, instead of me showing you this, let me show you the website I'm looking at. So I'm looking at NearEarth Objects. That's an object like the asteroid you mentioned, and it shows the closest approach. So 2 lunar distances, 1, and then less than a half of a lunar distance. So in between the Earth and the moon, right? So let's see. The dangerous part would be size, obviously, is one part. Mass would be really the corresponding piece. And then the relative speed, right? So the greater the relative speed, the more dangerous it could be. So some of these are getting pretty close. The largest ones are not, though, right? The largest ones are actually not getting very close. Well, no. Yeah, the largest ones don't get very close. Yeah. So anyways, yeah, let's see. The name of that one. So March 29th. This is the thing it's supposed to be. Is this it? No, this is not it. Well, that one's really close though. It's pretty big. Yeah, it's about 4 moon distances away. Okay. So yeah, I mean, that's pretty big. Let me just go ahead and switch back. Okay, it's time to start class. Hey, good morning, everybody. So I don't know if you notice any difference. I'm trying to stream in a higher setting and it's working, but I don't know if it's working. So we'll see if you guys can see me any more clearly. I can see clearly now. The rain is gone. Oh, it's very disappointing to not have your faces in front of me. But anyways, I can't see you, but I know you're there, and I appreciate that. And actually, thank you for all the emails. I do end up getting a lot of emails, but that's, please know that I want to talk to you. So if you send me an email, I will send back an email. If you don't hear from me, something's wrong. You might have emailed the wrong person. So remember, I'm SP Kelly at Pipeline, www.sbcc.edu. Okay, so let's talk about our class now that we've got started. Let me go back to our class and make sure that everybody is aware of what's going on. So let's see, I've got this in the mode here. We had a couple of crash courses to do this week. One was due today, binary and multiple stars. How many people did that one and got 100%? Anybody do that one and get 100%? Let's see, can I see? There we go. Good morning, good morning, good morning, good morning. Anybody do the crash course and get 100%? Anybody? Okay, and then we have another one on black holes. Oh my gosh, you guys are gonna learn about black holes. They're so awesome. And then of course we have an exam coming up. This doesn't quite work, does it? Well, what are we gonna do? I don't know. Well, some of you went already, so we'll see what happens. I do have a couple of extra credit opportunities coming up. People have been asking about that. One is gonna be if you wanna watch a movie. It's a really cool movie. I'm just gonna try to come up with something where you can write a little essay or something to let me know that you watched it. And then the other is going to be to see a guest speaker. So we are arranging, the Astronomy Club is actually going to be discussing today a guest speaker, UCSB grad student, one of our adjuncts, Jared Goldberg, is going to give us a talk, and it'll be online, of course. But if you watch the talk and give us a little feedback, I'll give you extra credit for that, as if you had come to a talk. So that means it's worth a little bit more because it is in addition to your regular class. I should mention also with exam 3 coming up, I think by the beginning of next week, I have to have it by then, never mind. By maybe later this week, I will have the advanced questions with the tutors. And so if you haven't gone lately, remember that you can go visit the tutors. If you go over here to the Pages tab, right, tutoring and PAL schedule, make sure that you click here to get the latest edition, and you can see how to meet up with them. You can meet with people later today, right, later today. Ooh, lots of options today, actually. And then tomorrow and Thursday and Friday, you've got options, okay? So be sure to click this link. This is a Google Meet. In addition, there is PAL sessions, and we have 2 sessions, one on Wednesday and one on Friday. And I did already send you a link. That will be the same link. I will send it out again to remind you. Actually, I should probably just put it here. Now that I think about it, I will put it here. I just will do that later. Okay, so add the Zoom session here. Let's see, what else? And finally, if you go to here, NetTutor, apparently this could work. Has anybody ever tried that? I'm curious. So I can't sign in because, let's see if I try to do this. Okay, and if we go down to astronomy, does it work? No tutor available. See schedule. Okay, well, here's our schedule. So today is 12 a.m. to 4 a.m. Okay, that's not very useful. All right. But anyways, Wednesday. Oh my gosh, the schedule is crazy. They are in another country. Okay, I guarantee it. Okay, so I'm not sure how useful that actually is now that I look at it. Anyways, all right, that's probably not going to help you very much. That's okay, no problem. We got our regular tutors. Okay, so I don't know that astronomy is very helpful for NetTutor, but anyways, hope you guys are doing okay, and we are getting some good news, right? It looks like Cottage Hospital has plenty of room for more people, and they're saying that the social distancing is working. So keep it up. We're doing a good job, and what you're doing matters. It means that we can be healthier, and not as many people are going to be impacted, right? Not as many people are going to die. So that's a really fantastic thing to hear. And our community is doing a great job at doing the social distancing. So let's get it done, right? Okay, and then we can move on. All right, so I am going to go ahead and begin the lecture. Let's see, does anybody have questions? I'm going to go ahead and look for any questions. Would love extra credit. PAL is so helpful. Oh, great. Okay, good. Happy to hear that. And thank you. And if you have questions, go ahead and put them in the YouTube chat, and I will take a look at them when we finish, okay? So we are ready to, we need to finish chapter 12. I just have a couple more slides to do. And then we will go ahead and begin chapter 13. Okay, so if you're ready, without further ado, click your clickers. No, we can't do that. Okay, let's take a look at chapter 12, the finish of chapter 12. So this actually is a young star cluster. Okay, so we have a name for this. Actually, want to make sure you write down the name. It's known as an open cluster. An open cluster is a young star cluster. Some examples, I'll mention an example in a moment. But we see lots of them. By the way, I'll talk about that in a minute. But anyways, a young star cluster is a cluster of stars that are born together, but are not going to be large enough mass altogether to bind together and stay together, which means they're going to separate from each other. So an example of a young cluster is the Pleiades star cluster. That is the cluster that shows up on the left. And so the left-hand side, we see the Pleiades star cluster. You can see the blue reflection nebula. It's beautiful. And it's young. So what does that mean? It's not old. So what does that mean? Well, it turns out that if you look at the HR diagram, there are some stars which have left the main sequence, right? Because they're very massive. Most of the main sequence is here, but if you look, we're missing the very lowest mass stars. Remember that along the main sequence, that mass determines where you show up on the main sequence. So our sun is right around here. Larger mass stars are up this way, and smaller mass stars are down to the lower end of the main sequence. So if you look, there's not very many stars down here because they haven't come. They're not there yet. So the smallest mass stars have not been created, have not made it to the main sequence. So this is a young star cluster. So it actually, this is a real star cluster, and you see that the real data is not quite so neat. So on an exam, I probably wouldn't give you something where things are missing from both ends. I probably just pick one or the other. But if I show you a picture like that, you want to recognize that if they're missing stars from the upper side, that tends to show the age, right? It's older. If they're missing stars from the younger side, then from the smaller mass side, then they are younger star clusters. So after a while, this will fill in, right? And then this will start to peel off, right? And you can find out the age of the cluster by where it peels off, right? What star has just left the main sequence? That tells you the age of the cluster. Now, really cool thing to know, our sun was born in an open cluster, much like this one, which means that it has sibling stars that were born together with the sun and are made of the same kinds of, have the same chemical ratios, but they are not anywhere nearby. They've drifted away, right? So our sun's brothers and sister stars have drifted away from it. That's actually Anna. That would be a good poem. Anyways, so otherwise, you know, our sun seems to be by itself now, and it is. It's by itself right now. Another cool thing to know is the Big Dipper is actually an example of an open star cluster. So we have the Big Dipper, but in 100,000, couple millions of years, we're going to start to see changes, and eventually there will no longer be a Big Dipper, right? A Big Dipper happens to exist right now, actually millions of years. Okay. So this is another really rich area of the universe when we look at it. So the Carina Nebula, so remember nebula is glowing gases, and it has, including one of the most massive stars ever studied, Eta Carinae, okay? So Eta, AB, alpha, beta, gamma, delta, epsilon, zeta, Eta Carinae. It's not the brightest, but it happens to be very big. So why do star clusters have a range of age? Meaning they're not all exactly the same age. Well, the supernova blast expands through the cloud and begins to form new stars. But the next generation, not next generation, but the next wave of stars that form is not exactly at the same time. They're going to be nearly the same age, but not exactly the same age. So it just takes time for the cluster, for the shock wave to propagate across the what is it called? What do you call it? Oh my gosh, interstellar, sorry, interstellar clouds, interstellar medium, sorry, ISM. So across this interstellar medium, across the cloud. So here is some more examples. This is the Eagle Nebula over here, which is pretty cool. So an elephant trunk is a linear feature at the edge of an H2 region composed of molecular gas. So these are cooler gases, and this is you can't see the nebula around it. And they point towards ionizing stars and gases. Okay, so one of the clues, we're going to talk about this after our next exam, is that we have these very bright stars behind the clouds that are causing them to light up. So they cause them to light up, but actually will eventually blow them away. So very large O stars, right? Very massive stars, very hot stars. O, B, A, fine girl, kiss me. These are the hottest stars, are actually radiating more ultraviolet photons than anything else. And they will cause these things to light up, but also to erode away. Blah, blah, blah. A newly formed O star will be surrounded by thousands of lower mass stars, thousands of them. Okay, so this is what's going on inside of the Orion Nebula. There's a tiny little feature that we can see sometimes, is a little tiny solar system that's actually being blown away by another star's solar wind. So Proplyd is a teardrop shaped knot. I don't actually think that's in your study guide, so you shouldn't worry too much about that. But it's kind of dangerous to live in the neighborhood of a really massive star. Okay, so stars in clusters tend to be born at about the same time as their siblings from the same event. Would you say that's true or false? About the same time. You see, it's got a little bit of room here to be not exactly the same time, about the same time. What would you say? And we're going to go ahead and say true. That's true. They're all born about the same time because they're made from the same shock wave. Okay, same shock wave. So I realized I actually skipped a slide I need to talk about. So I'm going to go back and show you one more slide. Just give me 1 second. I messed up just a little tiny bit. Sorry about that. I realized I wanted to talk about this. Okay, so let's take a look at this slide one more time. This is a really important thing for you to see. Sorry, so that's why I wanted to go back and do it again. Okay, so here we have the CNO cycle, and we've had some questions about this already. So this is a more efficient cycle for doing nuclear fusion. And remember that it's doing the same, net process, taking 4 hydrogen atoms, actually not atoms, nuclei, 4 hydrogen nuclei, and combining them into 1 helium nuclei, right? That's the same as PP, right? 4 hydrogen become 1 helium. Remember that the mass of the hydrogen is greater than the mass of the helium. The missing mass is turned into pure energy, which powers the star. But if you look at this, you want to understand it is more efficient, right? Which means it can happen at a faster rate. But it needs to be a hotter core, right? A hotter core temperature. So it doesn't happen very effectively in smaller stars like our sun. Now, does it happen at all in our sun? And the answer is absolutely yes. Okay, so I want to make a little note to you. Okay, this is kind of important, right? There's a question on your next exam. So here's the question, right? Which process occurs in a star? P, or CNO? Which one, right? So which is the question? So is it A or is it B, right? Is it A or is it B? And the answer is C, both. Okay, I tricked you. Sorry about that. So both processes are happening inside of every star, right? Whether it's a big mass or a small mass, both of these are happening. However, when you talk about where does most of the energy come from, it turns out that a star will prefer one or the other depending on the mass, okay? So if I do a number line right here, and I have, our sun, I've always put our sun in just to give an idea. Our sun actually prefers, or the balance is going to be more coming from the PP process, right? Proton-proton combination. It turns out that the dividing line right about here is 1.4 solar masses. And if you're less than 1.4, PP is going to give you more of your energy. If you are greater than 1.4, then the CNO is going to give you more of your energy. If you are 1.4 solar masses, then 50% comes from PP and 50% comes from CNO. Does that make sense? So it's not one or the other. It's a gradual change from one to the other. And 50% energy comes from PP, 50% CNO in a 1.4 solar mass star. But as you slide one way or the other, that mechanism will dominate inside of the core of the star. And it's primarily a temperature difference, temperature, maybe density as well, okay? So I'm going to ask you that question. I'm giving it ahead and giving it away. What process happens inside of a star, PP or CNO? And the answer is both. Okay, great. So now we are done with chapter 12. Oh, no, sorry. Oops. I'm so funny. I forgot one more slide. Okay. What happens if you don't have enough temperature to do either PP or CNO? Then you fail, right? You are not a star. You are known as a brown dwarf. Make sure you know the name because it's on your study guide. It's one of the names that you're supposed to know. A brown dwarf is a failed star that has too little mass, right? So it never reaches that temperature of 15 million Kelvin to be able to start the fusion. And so it has less than, this is the reason, right? It has less than 8% the mass of the sun. It's underneath the minimum mass that you need to start the fusion chain reaction. Okay, so astronomers believe that there are approximately 100 billion brown dwarfs. There's a lot of them, okay, in our galaxy. There's just a lot of them. So that's kind of an important idea. There's lots of these little failed stars. Now, some people think that Jupiter is a failed star. Did anybody ever get that message? Maybe anybody get the message that Jupiter is a failed star? Because I think that's kind of funny, and I'll explain why in just a moment, right? Does anybody know the mass of Jupiter, right? So in terms of the sun, what is the mass of Jupiter? The mass of Jupiter. So sometimes people said our sun could have had a companion, right? It could have been a binary star, but it turns out the mass of Jupiter is about 0.001 solar masses. So as you can see, it is much, much less. It's much, much less than 0.08 solar masses. There is no way that Jupiter could have become a star. It would have taken about, what do I need? 80 Jupiters is finally going to be the smallest red dwarf, right? It would take 80 Jupiters just to get a single star, right? So Jupiter was not even close to having enough mass. Sorry, Jupiter, you were never going to be a star. Okay, now here's a crazy thing to know. Does nuclear fusion ever occur inside of Jupiter? And the answer is yes. Occasionally, we see flashes that indicate that nuclear fusion, an event has occurred, but it's not sustained, right? It's just kind of like one super energetic proton smashed into another super energetic proton. It was just kind of a happenstance, a lucky little situation. I don't know if it's luck, but whatever, it happened. And we see a signal, but it's not a sustained fusion. Jupiter could never be a star. Okay, so that is chapter 12. I am done with chapter 12. It's 8:23. I'm not that far behind schedule. So chapter 13 is our next up, and This is going to be fun because we get to finally talk about how stars die. I mean, this is exciting. This is a really exciting part. Okay, so Phil talks in great detail about how stars die. Some of the details that he talks about, by the way, he gets very animated. And it turns out he was his specialty in graduate school, he got his PhD in red giants. So that's actually one of the reasons why when you were listening to him, he got so animated. I don't know if you noticed, but he got particularly animated, and he was actually talking about his dissertation research. Okay, so we are on to how do stars die, right? So stars live, stars are born, stars live, and stars die. And the key thing to all of it is how much mass, right? The mass of a star determines everything. A more massive star will form very quickly, become a main sequence star very quickly. It will live its life very quickly, and then it will die in a very dramatic way. A smaller mass stars will take a long time to become a star. It'll spend a long time falling, collapsing, and finally become a protostar and then a star. And then will live an incredibly long time and then finally die in a very soft and gentle way. So our sun took a little while. It turns out the numbers are a little bit fuzzy. I went looking for hard numbers on how long it takes to become a star because some of you asked that question. And what I discovered is that we don't really know for sure. We just know that there's a big difference. We have seen some stars in the midst of formation. We see a number of stars forming and different mass stars too. But it's still, there's not a lot of information yet about the exact timing. So it just takes a while, right? I mean, we have models, but they're not perfect. Okay, so here's a word that you need to know: supernova, a highly energetic explosion of a massive star. Okay, so this is going to be an exciting event. And actually, we talked about how the death of a star in a supernova actually generates the next generation of new stars, right? The shock wave of the supernova is going to lead to the birth of new stars, which is kind of a beautiful idea, right? We see it in the world around us. When things die out in nature, they become fertile places that lead to the birth of new things, right? So it's a cycle of birth and death that we see out in the universe as well. So how do highly energetic explosions of massive stars occur? So we want to talk about that. So the concept of what we're describing is known as stellar evolution, right? How do stars evolve in their life? And the idea is that we will see that not all stars die in exactly the same way. Some are going to be more dramatic. Some are going to be much more gentle, right? So stellar evolution, the gravity pulls stars together. The energy released via fusion is how it fights against gravity. But at the very end of its life, a star will explode and send a lot of mass back out into space again. And just a tiny little core of material will remain behind, right? So if you read this sentence right here, it's more important than you realize. Stars return much of their mass. And if you want to write down a number, it turns out maybe up to 80% of the original mass gets sent back out into space, right? 80%, that's a big number. I know it's kind of hard to understand, but I want you to think about that, right? That what's left behind when a star is dead is just a little tiny ember of the original star, right? A tiny little seed, not a seed, but a tiny little piece of the original mass is left over. So we have already looked at this before, but the more massive a star, the less time it will spend living on the main sequence. This is main sequence life. So they don't even have the 100. Everybody remember the 100 solar mass you're supposed to memorize? 100,000 years. 32 solar masses, 2 million. 16 solar mass, 10, right? One solar mass, 10 billion, but 1.5, 3.6, 2, only 2 billion, 1.8 billion years old, okay, before it leaves the main sequence. Okay, so why does the star live such a little amount of time when it has such great mass? And the idea is that it's burning its mass very quickly, right? It's doing nuclear fusion. What mechanism would be used for fusion with a very massive star? And the answer is predominantly CNO, right? Much more energy comes from CNO, which is a more efficient process. So it means it can do it in a faster, more efficient way, more energy comes out. So the larger the mass, the more energy it will produce in the core because it's able to burn its fuel faster. As a result of that, what happens to the surface temperature of a larger mass stars? They're going to be much hotter, right? We already knew that. So which star has the longest life expectancy? So you're going to see a question just like this on your exam. And of course, on the quiz that you have to take later this morning, once I finally publish it, which star has the longest life expectancy? You can think about that for a moment, but it's pretty simple to answer that question. The answer is the smallest mass star, right? Smaller the mass, the longer you get to live. Okay, so we're going to try to understand, first of all, what happens to a smaller mass star. Smaller mass stars, like our sun, right? What's going to happen to our sun? You should definitely know what's going to happen to our sun, right? That's an important story to be able to tell. You're taking an astronomy class, you live near a star. What's going to happen to that star in the future? Okay, so let's take a look right here. This is the, actually, I think, you know what, actually, I'm going to stop for a second. I like to talk about this on the board. So let me switch to the board right here, right? So what happens, right? What happens when the H in the core, what's H? H is hydrogen, right? Is depleted, right? What does depleted mean? It means it's not there anymore, right? So we've run out of hydrogen in the core. We've run out of fuel. Run out of fuel. So meanwhile, how did this work, right? Actually, the way it worked is you took 4 hydrogen nuclei, you formed one, you don't usually put a 1, but I'll put it anyways, 1 helium nucleus, but there's some leftover mass that's missing mass, and therefore you also get some energy, right? This is the process. So this is our fuel, right? And what the fuel creates is called the ash. Okay, the ash. The ash of the fusion reaction is what is being made by the fuel. So is this fuel? And the answer is not at first. So as hydrogen, the amount of hydrogen goes down, right? What happens to the amount of helium? Well, the amount of helium is going up, right? It's getting enriched in helium. So the core is changing composition from a mixture of hydrogen and helium to becoming almost pure helium. So you might be like, wow, that's cool, right? We run out of hydrogen. What's happening? Let's switch to helium. Yeah, why not? Let's do it, right? Let's switch to helium. But if you go back to the story of why is fusion so difficult? By the way, we're trying to do fusion on Earth in order to produce limitless energy, right? It's going to be this amazing thing. And they've been trying to do it my whole life. And I've been waiting for it to happen. It may be closer than ever, but it's still not here yet. But why is it so difficult to make fusion occur? Why do you need to give it such high temperature, high velocity? And the answer is because hydrogen is positive. Hydrogen is positive. They don't want to go together. You have to smash them together at a high velocity. So the velocity comes from the temperature, right? Right, capital T. The higher the temperature, the faster the speed of the ions, right? The faster they will travel. So if you can get them close enough together, right? Remember that the strong nuclear force will bind them together and they become a single nucleus, right? The strong nuclear force. But it only works on a very short range. So remember the temperature that we needed, by the way, it was about 15 million actually, it's not quite 15, but I mean, that's what we, no, sorry, 10 million. Sorry, I was wrong. It's 15 million now. It's 10 million Kelvin, okay, to do hydrogen fusion, okay? Okay, but that's because hydrogen is just a +1. What happens when you try to do helium fusion? All right, so this is exactly what I would have done on the board with you, right? So if you try to fuse helium, let's try to understand why does it not want to go together, right? Well, helium is larger, by the way. It's 4 times as massive, but it has a charge of +2 and +2. So how do helium ions feel something for each other? And the answer is, well, they repel each other, right? They don't like each other. And so if you want to get them to go together, you need to smash them together, but not at the speed that we had to do before. Because if you look at these +2 and +2, how strong is the repulsive force? The repulsive force, which is, by the way, the electromagnetic force, is 4 times as strong, right? 2 times 2 is 4. So what does it mean, right? If you want to do helium fusion, no problem. You just have to speed it up, right? You need to go, but you need to go a lot faster to make them fuse. And in fact, the helium fusion occurs at about 100 million Kelvin, right? Oh, why did I put capital M? I don't know, whatever, 100 million Kelvin. So this is a big jump, right? To go from 10 million to 100 million is a big jump. So what happens to your helium core, right, is now full of helium, right? What happens to your helium core? Does it start fusion, right? So if you remember, right now it's about 15 million. So does it start fusion? Well, no, it's not hot enough. So if it's not fusion, then what's happening is you're not creating energy inside here. What's going to happen to the radiation pressure? Is the pressure going to be big enough to hold back gravity? And the answer is gravity is pushing in, but now, because we're not doing fusion anymore, the radiation pressure is not going to be able to stop gravity, right? The force of gravity is going to be bigger than the pressure inside. What's going to happen is it's going to shrink, right? It shrinks the core. And so what happens then, right? So this is what most people are confused by. With shrink the core, what happens? As you shrink the core, you heat up. Because you're compressing a gas, you heat up. But you see, you've got to get up to 100 million Kelvin. So it doesn't matter that you heat up a little bit. That's still not enough. You need to heat up a huge amount. So guess what? You still don't start fusing the helium, but what happens is this place outside the new core is now hot enough to fuse the hydrogen, right? The hydrogen around the core is now hot enough. It's hot here, now hot here. It's greater than 10 million, right? It used to be cooler than 10 million. That's why it wasn't fusing. But now that the core has heated up, it's hot enough here to begin fusion. And so you get a shell of hydrogen fusing. It's called hydrogen shell burning. Okay, so by the way, there's a lot more hydrogen in the shell than there was in the core. I know it seems strange, but this actually produces much more energy than the core ever did. So we've got this very interesting situation. If we're fusing more hydrogen than before, then what happens to the amount of pressure? And the answer is there's much more radiation pressure than before. The radiation pressure increases. It's actually much bigger than it was before the collapse. And in fact, the star expands, right? It expands to try to get to a new equilibrium, to reach a new equilibrium, hydrostatic equilibrium. And so what have we just entered? We have entered the first part of the red giant phase, right? The sun becomes a red giant, okay? So I'm just, sorry I'm late. Actually, if you are late and you're coming in late, don't worry. Just go back at the end of the video and then start it again, and it will begin. Can we start over? That's so funny. But anyways, don't worry about it, right? If you come in a little bit late, just go back after the video is over and it'll be recorded and you can watch it from the beginning, okay? Don't worry about that. However, there may be some questions on the quiz afterwards that you need to know, okay? So we are in the red giant phase, and let's go ahead and go back to our video, back to our picture here. Let's see, where is it? Chapter 13, okay. So we are looking at this new thing right here. This is called hydrogen shell burning, okay? So if you notice, where is the fusion taking place? It is not taking place in the core, it's in the shell, right? So is this a main sequence star anymore? And the answer is not anymore. This is not a main sequence star. It has left the main sequence. So sometimes people ask that question, why did the star leave the main sequence? Well, the answer is because you can't do what main sequence stars do, which is turn hydrogen into helium in the core. And the reason is you ran out, right? Once you run out of hydrogen fuel in the core, you stop being a main sequence star, but you will expand, okay? Now, we don't know exactly how big it's going to be, but it looks like the sun is going to be quite a bit bigger than it is now. And this is, again, because you're producing much more energy in that shell burning than you did before. Now, keep in mind that what's going on in the core? What happens to the core? Well, the core actually continues to collapse because it's still not hot enough, right? It continues to collapse. But there is a very interesting thing that will happen. Eventually, the core will collapse to a tiny little core, and that core is now going to reach 100 million Kelvin. Okay, so the core, so let's write this down. The core during this red giant phase, can you read this? There we go. The core continues to collapse and heat up, right? And one day, right? One day, it reaches 100 million. And so what happens? The helium begins fusion, right? And we call this the helium in the core, right? In the core begins fusion, right? Begins fusing, I guess, begins fusing. And we call this the Helium Flash. So what do we have? We have two things going on inside of our red giant. We have the hydrogen shell burning, plus the helium core burning, and they're both producing energy. So what does this star do? Now that it's got so much energy being produced, what happens to the star? And the answer is it expands even more, right? It becomes an even larger red giant. And so I've got some news for you, right? The sun, you know, normally over here, we got our planets, we got Mercury, we got Venus a little bit further out, right? Venus, Earth, we're pretty safe out here, right? But here's the idea. When we get our first red giant phase, I think Mercury is already going to be inside of it. But as it expands, in the next red giant phase, the sun is actually going to get bigger and eventually eat up the Earth. And it's not quite going to get Mars. Mars will be safe. Mars is safe. But unfortunately, the Earth is going to end up inside of the sun, right? That just blows my mind, but it turns out that the sun is going to eat up the Earth. I don't know how, but that's what it says. Okay, so that's what the numbers say. As hard as it is to believe, that's what's going to happen. So let's take a look right here. So I need you to look at this picture right here of the HR diagram. And we want to discuss what you're supposed to be able to interpret. Now, it's kind of curvy and interesting, but what I want to do is not worry too much about that. I want to just kind of reduce it to a simpler kind of motion. So when you look at this diagram, remember how it works. We've got O, be a fine girl, kiss me along the bottom, which is the temperature scale. And so it's going from the hottest stars on this side to the coolest stars over here. On the vertical scale, we have absolute magnitude, or in this case, luminosity. So the higher you go, the more luminous the star is. Okay, so everybody understand that. So what happens as you move from 1 to 2, right? So when you look at this, when you see something like this, it's almost horizontal, right? It's almost horizontal. You need to be able to interpret that. And then here's this one right here is almost vertical, okay? So I actually am going to stop for a second and show you what you need to be able to do, right? You need to be able to describe changes or when you move in the HR diagram, right? So what you want to do is describe a path on the HR diagram. Okay, and there's two kinds of paths, right? Either a horizontal or vertical, right? One or the other. Got to be one or the other. Okay, so I'm going to draw, my simplified HR diagram, right? We've got the luminosity measured in terms of the luminosity of the sun, which means there's a 1 right here, 1, and the luminosity is going up, and then we have here. I'm going to do the temperature thing that you're supposed to memorize. O, B, A, fine, giraffe, kiss me. Okay. O, be a fine giraffe, kiss me. Okay. And so the main sequence looks something like this. Okay. Doesn't have to be perfect. And then you go over here to the 1, and if I did this right, it goes down to the G. Supposed to be G2, but anyways, okay, pretty good, pretty good. Okay, so that's our sun right here. This is our sun, the sun. Okay. So what's going to happen to our sun? Well, we saw that there's actually 2 different things. It's going to go over like this, right? So I want you to describe what's happening, right? So we go from 1 to 2. What's going on as you go horizontal, right? So horizontal movement from 1 to 2, right? What's going on? So we're moving horizontally. What's changing, right? This is, sorry, I forgot to put temp, T in Kelvin, right? Temperature, T. I should have just put T, sorry. T in Kelvin. T in Kelvin, okay. So what's going on as you go from 1 to 2, right? And the answer is you are cooling off, cooling, right? This is the surface of the star. How is the surface of the star cooling? How do you get cooler? Well, think about that for a second. All right, now take a look right here. What's happening to the luminosity? It's cooling, but the luminosity is constant, right? It's not changing. How is that possible? Because if you remember, I know this is going to be a big jump, but if you remember the luminosity formula, it's got a constant. We could ignore that, but just it's in there. You have big A, which is the surface area, which is, by the way, 4 pi r squared, right? And then you have temperature to the 4th power. Okay, so this looks complicated. Try not to get too worried about it. The idea is, what if this gets smaller? What should happen to the luminosity? Well, it should get smaller too. And if it doesn't, there's only one way. How did that happen? Because this gets bigger. When this gets smaller, this part gets bigger. The star expands. Well, that happens to also explain how it cools, right? So the star expands. It's cooling and expanding. Now, if I did see something in the other direction, right? What if I went from horizontally from 2 to 1? I know I didn't do that in this picture, but I just want to think about it. What would be happening? It would be heating, and getting hotter means T is getting bigger. But if the luminosity is not changing because we're going on a horizontal path, how do you get the same luminosity? You have to be a much smaller star. So heating and contracting would be the answer. All right, so horizontal path is either going this way, getting cooler and expanding, or can you guys hear me? Okay. I can see that I lost audio there for a minute. Hopefully, can you let me know actually what you guys could hear? Did you hear me talk about, actually I wrote it down on the paper, so hopefully you got that. You can't hear me. Can you hear me now? Can you hear me now? I'm pretty sure you can hear me again because I see my microphone wiggling. Okay, so if you look at the horizontal path, the idea is that on the horizontal path, if you go from 1 to 2, you must be cooling, but also the star must be expanding in order to keep the luminosity the same. If you go backwards from 2 to 1, right, then you're heating up, but you have to be getting smaller to keep the luminosity the same. Okay, so I've just explained that anytime you see a horizontal motion, that's what's going on. So what about vertical, right? So let's go and make a vertical line. Okay, and we're going to put a star up here, or a final star up here. And by the way, you'll notice that I'm supposed to be above, let's say, the letter M. So we might know the name. It's called a red giant. Our sun will never get bigger than a red giant. It's a red giant when it's done burning hydrogen. But what is it? What's this called? A 3. Okay, so what is the vertical motion? I'm going to put down here vertical. So let's say I go from 2 to 3. What's happening to when you're on a vertical line? What's happening to your temperature, right? What's happening to your temperature? And so we know that we're above the same letter of the scale. So what does it mean? The temperature is constant, right? It's not changing. So look at our formula. If temperature is not changing, but you're going vertically, what's happening to your luminosity? Your luminosity is increasing. How is that possible, right? So if this is not changing, but this is getting bigger, then it must be this that's getting bigger, which means R is getting bigger. The star is expanding. Okay, so the temperature didn't change much, but the size R increases, right? The star is expanding. What if you are moving from 3 down to 2, right? If you do it in that direction, same thing, temp is constant, but now you are lowering luminosity. I can write more neatly. Luminosity is decreasing. So why is that happening? The star is contracting. Okay. So we now have described very simple, either horizontal or vertical motion on the HR diagram. Okay, so those are the things that I expect you to be able to do. Now, in real life, it turns out sometimes it even goes on a diagonal, right? So, you know, what happens then? Well, you have to, don't worry about it. You have to be an astrophysicist. So we're going to talk about, you know, horizontal or vertical changes, and don't worry about the fact that it's not perfect. Okay, so here we see. This is known as the red giant branch because our sun is becoming a red giant. Okay, and we understand why. Why is it? Because of the extra energy that is being produced in the core of the star. Not only is it fusing the hydrogen in a shell, it's also fusing, well, actually, we didn't quite get there. So we're going to see that there's a second stage, right? So I'm going to continue. And at some point, right, we said the core helium begins to ignite. So it says here between 2 and 3, we're getting this ignition. And so that's really what's driving this upward movement, right? Because this extra energy that the helium produces, right, has to go somewhere. And it turns out to establish a new equilibrium, the radiation pressure being so much greater, it pushes the outward on the force of gravity is bigger than the force of gravity for a while. The star expands, and as it does, it cools off. So the surface temperature becomes cooler, and we end up with a stable red giant star. Okay, so helium core burning happens faster than the hydrogen main sequence. There's a lot less fuel at this stage of the game. So let's see, I need to tell you a story. So let me see if I can find something. I want to show you guys something, right? So actually, I should just show you what I want to show you. Okay. So let me just show you this. This is an incredible page on Wikipedia called stellar nucleosynthesis. Please write that down, stellar nucleosynthesis. And it means, if you read it, stars, stellar, nucleosynthesis means, synthesis means to make, right? So making nuclei, right? How do stars make nuclei? That's literally what this means. And we know that the Big Bang produced mainly hydrogen and helium, a little tiny bit of lithium, okay? But really hydrogen and helium. And the hydrogen is always the first fuel, okay? Here's a chart kind of showing you how a little bit past our sun is where you finally get the crossover to CNO, right? Way too much information. Oh my gosh, I want to talk about this in a minute, but not right now. I want to show you some, oh, never mind, it's not working. Okay, hold on, I'm looking for, maybe I should just look for fusion. No, I want to look for more. Helium fusion, okay. I guess I have to. Oh, here we go. This is what I wanted to show you. So the hydrogen is the first fuel. Helium is the second fuel. And then we start getting some other fuels, right? So lithium is not very common for stars. It turns out carbon, neon, hydrogen, oxygen, silicon. So actually, I guess this picture is the best picture. We've got hydrogen, helium, carbon, oxygen, neon. These are shells of burning in a very, very massive star. And so the idea is, I'm going to go ahead and stop the share and go back to paper again. So we know that the hydrogen fusion occurred at 10 million Kelvin, and helium fusion occurs in at about 100 million Kelvin. But what happens with helium fusion, right? How does it work? So helium is element number 2. Okay, element number 2. And it turns out something very interesting happens, that you don't just get helium plus helium. It doesn't actually work out very well to do that. Another name for this, by the way, is called an alpha particle. I think we've already talked about that, but I just go ahead and remind you again. So it turns out that a very common process in this sun-sized stars, to take not just 2 of them, but 3 of them. It's called the triple alpha process. So instead of getting element number 2 plus 2, element number 4, what happens if you take 3 helium nuclei and combine them? What do you get? And the answer is you get a carbon. You get carbon. Carbon, I mean, if it's truly completely ionized, it will be 6 plus because it's element number 6. Again, plus some energy, right? Plus some energy being released. It turns out that some of the carbon will also combine with an alpha particle and form oxygen and release some energy. So fusion, this is what you need to know. Fusion of helium makes carbon and oxygen ash, right? This is a fuel. Then you make carbon and oxygen ash. So again, take a look at the carbon right here. What's the temperature needed to begin carbon fusion? What is the temperature needed? It is 500 million Kelvin. Wow, that's a big jump, right? Remember, helium was 100 million. So to do carbon fusion, you're going to need 500 million. So again, what's going on? The helium is fusing, the fuel is fusing, and making carbon ash, which is gathering in the core. So in a sun-sized star, right? Sun-sized star. So it's making carbon and then a little bit of oxygen too. So carbon and oxygen are being made. And at some point, you're going to run out of helium. By the way, the hydrogen shell can continue burning because it's not burning quite as fast. But this is a very rapid process. Okay, so I'm not going to tell you the number of years, but I want to tell you, but I feel like it's too much detail. It's probably only about 100 to 150 million years until we run out of helium. But the red giant phase, this is actually something you're supposed to know. The red giant phase for our sun is about 1 billion. I capitalized it again. I don't know why. 1 billion years. Okay. So remember 10 billion for the main sequence life, and then another billion years as a red giant. Okay. But it is going to run out of fuel. So what happens to the core when it runs out of fuel? So the core shrinks and heats up. And it heats up and eventually gets to 500 million, right? Well, the answer is no. It never gets hot enough. Not ever hot enough to use carbon and oxygen as fuel. And so our sun will die. It will be the end of the life of our star. Okay, so that is an important element of our sun, right? It can use hydrogen as a fuel. It can use helium as a fuel for about, the hydrogen and helium will last for about 1 billion years before it finally just shuts down, and then it's done, okay? So let's take a look right here at the next stage. There is this period where it has burned through the hydrogen and helium in the core, so the helium is now done, but it's still using hydrogen in a shell. And it's actually even, so you can take a look from 3 to 4, what's going on. It's actually getting hotter and decreasing in luminosity. That's actually fine. It had to, actually had to shrink, right? It shrunk a little bit. And then 4 to 5 is a vertical thing again, right? So it's nearly the same temperature, but it actually has expanded again. So it's even larger than it was before, okay? So this thing is huge. Remember I told you that our sun will end up being, look, over 100 times the radius of the sun. It's gonna stretch out and encompass the Earth. The Earth will get eaten up. And so this process of being a red giant is gonna be a huge star. So the outer layers of the star are actually going to be very loosely held by the star. Something interesting is gonna happen. We're going to see that anytime the star kind of does a little hiccup or a little extra energy or anything at all, that it blows away a shell of material. And the shell of material is going to move away from the sun, right? So it turns out that in this stage of its life, the sun is actually going to shed layer after layer of itself. And again, it's hard to understand how much, but it turns out that it's going to shed almost all the way to the core. It's going to lose about 80% of its mass in this stage. So this material is being driven off, and this picture that you see right here, this is a picture of something called, you should write this down, a planetary nebula. Now, there's something in the middle still that's actually going to be making this light up. So these shells of material that are moving away are the outer layers of the star, and then gradually getting lower and lower, it's still always the outer layer that's blown away because of the fact that gravity is so weak, and anything that happens inside of the star can just kind of push it. So it's like blowing bubbles or something but using its own body, it starts blowing them away. Now, this is a little more interesting. You'll notice that it's not a sphere. It's got some interesting structure. So the answer to the question, why does it have such an interesting structure? Nobody really knows, but we have some ideas, okay? So there's a couple of ideas. It could be one of the answers is that as a star expands, it eats up its planets, right? And if there's planets that it's eating up, those planets will stir the interior of the star and actually cause an asymmetric shell to form, perhaps, right? That could be one explanation. Another explanation is that the star is not by itself. It has a companion. And the companion is causing a deformation of this cloud to occur. And there's a third one that I can estimate or use as an idea. The star may have a very powerful magnetic field. And if that has a very powerful magnetic field, it may lead to ejection of material along the axis of that magnetic field. So some way or another, we don't know exactly how, but we get a not symmetric shell of material. Sometimes they are symmetric, by the way, but these beautiful pictures that we see are the planetary nebula. Except I didn't finish the story, right? How do they light up? So the shells of material are actually not going to be lit up until the very end. And so if you look right here in the center, there's a tiny little white dot. What is that? And the answer is that is the dead star, right? The core of the star, right? That little 20% of the star that was left over is going to form a tiny little ember, which is called a white dwarf. So our sun, once it runs out of the carbon, once it runs out of the helium in the core, our sun, you need to know that after our sun runs out of helium and hydrogen, that it is going to finally collapse to form a tiny little ball of hot matter called a white dwarf. Okay, so this is going to be made of what? What is the white dwarf? The white dwarf for our sun, right? Our sun's white dwarf is going to be made entirely of carbon and oxygen. Okay, probably more carbon than oxygen, but made of carbon and oxygen, nothing else. Okay, made of carbon and oxygen. And it's a really interesting thing. I want to talk about that in a minute. But before I do, let's make a little time for the life of our sun. Okay, so I actually want to think about this. I want to make a timeline, right? So from 0 to 10 billion, 10 gigayears, that's the main sequence, right? Okay, that's the main sequence, 10 billion years. But there was actually a stage before it became a main sequence star. It's pretty short, right? I don't know exactly how long, but it's pretty short, very short. What stage was it before it became a main sequence star, right? It's a star. And some of you know the answer, but there was a very brief protostar period, right? So it was a protostar, very brief. I actually think I've exaggerated. It should not even be this big. It's very, very small. So this is an exaggeration. It's even smaller than this. And then what happens post main sequence, right? For about 1/10, I've got to figure out, this is 1/10, right? For about, so we're up to 11 gigayears now, right? This is our red giant phase, right? This is our red giant phase. And then for a very long time, for the rest of eternity, well, not quite, but for a very long time, it's going to be a white dwarf. Okay. Now, I actually can't draw long enough, but let's say that I go and I continue on the next line, right? It's white dwarf, right? White dwarf. This is going to last a very long time. It's, by the way, cooling off, right? How is it cooling? It's cooling. Actually, I meant to put it in parentheses. By what process? And the answer is by radiation, right? It's cooling off. Eventually, it will cool off. And eventually, I have to go probably a whole bunch of times. Eventually, it will become a black dwarf. Okay, eventually. It's going to take a lot of times. And so this is going to be a cold ball of carbon and oxygen, right? It doesn't have any heat left. But it turns out there are none in this universe. There are none yet. There are none yet. Because it takes more than 13 billion years to make this. In fact, it may even take hundreds of billions, if not a trillion years. We don't know exactly how long, but it's going to take a very long time. There are no black dwarfs in our universe yet. Okay, so if you think about that, that will be the last stage, and that will last for the rest of the length of the universe, right? However long that lasts. So the black dwarf, I can't draw, but it's going to be forever, right? After that. Okay, so that is the life of our sun that you're supposed to know. I have a few more minutes. Let me keep going. Okay, so the hot little ball in the middle of this picture is a white dwarf. What does it mean? Well, it's a really hot little star. In fact, it's so hot, it's white, right? It's really white hot. It's radiating more ultraviolet than anything else. And so the ultraviolet light is shining out and it's hitting the clouds of gases that are moving away from the star or where the star used to be. And for a little while, they're lighting up. So these planetary nebulas, we think, are actually short-lived. because the cloud is continuing to expand. Eventually it will get far enough away and dispersed that you won't see it anymore. So we think that these planetary nebula only really last for, 500 to 1,000 years. They don't last very long. And so they're kind of these beautiful temporary things at the very end of a smaller mass star's life, right? A smaller mass star's life. And in the middle of them is the white dwarf that makes it light up, okay? Okay, so this guy, Charles Messier, some of you in the lab have definitely heard about Charles Messier. He was famous for his Messier objects. And the Messier objects are a list of 110 cool objects that we might want to look at in the night sky. There are a whole variety of objects. Stars always rotate. Yes, all stars rotate. And so that's actually how, that was a question, I'm sorry. Do stars rotate? Stars all rotate. And the smaller it gets, the faster its rotation should be. In fact, that's one of the mechanisms that we can think about for generating a magnetic field. Okay, so back to my slide. I don't know where I am. I think you guys can see me. Okay, good. So what is he known for? He was actually a comet hunter. This is a fun story, right? So Charles Messier had heard and knew about this very famous comet. You guys know about this, Halley's Comet. And that prediction by Edmund Halley, even though he never got to see it come back in 1756, I believe, was very important for Charles Messier. He wanted to do the same thing. He wanted to find a comet and have it be named after him, right? He would predict that it would return, and then it would be called the Messier Comet. And so he spent his life looking for a comet that would make him famous. And what do comets look like? When they're far from the sun, right? When they're not close to the sun, when they're not near perihelion, they're not very cloud, they don't have much of a coma. Remember that the coma is this cloud that appears when it gets closer to the sun. But if you do see them, they look like fuzzy stars. And so Charles Messier spent his time looking for fuzzy stars, and he found a bunch of fuzzy stars. And so he would watch them night after night, and he was frustrated because these fuzzy stars wouldn't move, right? If you're a comet, you're orbiting the sun. And he found all of these funny fuzzy comets that look like fuzzy comets. They look like, I'm sorry, fuzzy stars that weren't moving. They were definitely not comets. And so in his frustration, he began to keep track of them. He made a chart. He says, like, let me make sure to not waste my time watching this fuzzy star again. And so this list of objects that didn't move but looked kind of like comets became known as the Messier list. And what are they? Well, they're actually awesome. They're beautiful. There are a whole variety of things. Number one right here is called the Crab Nebula, and it's a remnant of a supernova. That'll be awesome. We have clusters. We have, here's the Pleiades star cluster right here. We have nebulas, M42 and M43. Here is a planetary nebula called M57, the Ring Nebula. And then, because his telescope was not good enough, he didn't realize that some of the things that he was looking at were galaxies, right? So we have all kinds of really neat objects. And so there's a fun thing that we often do. We didn't get to do it this year, but in the past, it's called the Messier Marathon. And it turns out the new moon, right? We want a dark sky nearest the vernal equinox. You can go out and actually see nearly all of the 110 objects. And so we have done this many times with the Astronomy Club. And a couple years ago, we set our record. I think my record is 63 objects in one night. And then what happens inevitably is the students say, can we go home now? Because it's like 3:30 or 4 o'clock in the morning and they get tired. I have never stayed out as long as I wanted to, but one day I will do it and I will see 110 objects in one night. Anyways, okay. It's kind of a fun thing. So we're going to go ahead and continue our evolution of our sun. We want to get to that point where it actually becomes a white dwarf. So if you take a look right here along from branch 5 to 6, what's going on? The outer layers of the star are being ejected, and those are cooler layers. So by the way, the star, what we see is heating up, but it's not really changing much in luminosity. And the reason is because you're looking at a smaller object, right? We've ejected the clouds of material, the outer layers of the star, and we're continuing to eject. And then finally, the star collapses, right? So we get a white dwarf in the middle, and we get a yeah, this has got it's a shockwave of wind. You don't need to worry too much about that. But the main thing is the ultraviolet light is going to create these beautiful clouds called planetary nebulas. So what is making the shape? So there's a couple of things again, right? We mentioned it could be eating up planets. It could be a binary companion, and it could be an accretion disk, which creates a magnetic field, which is making the jets, right? So north-south jets kind of make sense when you see that, right? That would be magnetic field, perhaps. Okay, so there is actually, and I think I'm gonna probably have to stop. Oh my gosh, how much fun. Okay, so we'll continue talking on Thursday about a very exciting dynamic, which is this thing that we've talked about before, red giant white dwarf companion. And we will talk more about that on Thursday. So I think I'm going to go ahead and stop the lecture for the day and say goodbye. Okay, so thank you guys for being here this morning. I'm going to make some questions based on the material we just covered, and I'll have that posted within an hour or so. And then you can take that quiz. And I still have to go and read the rest of your feedback. Thank you, all of you who posted. I really appreciated that. I've made a note, and then I'm going to go back and add those points. If you didn't do that, if you didn't post in the discussion section last week, then you are going to find out you didn't get some points. So if you get a chance to do that, please do that, and maybe let me know. Well, actually, I'm still looking, so I didn't quite finish. Let me see if there's any questions. Any questions? Have a wonderful day. Thank you for your attention, and we'll see you guys on Thursday. All right. Thank you. Bye. 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 Aw. Bye. Wave. Okay. Let me stop the live